got there in the end. Prior to setting up my own business, I was principal development engineer for LU, like any other job they gave me. Had about sort of 15 years in LU. And on being given that job up the day after I got it, I got told that they couldn't use the existing track form because the HMRI had said that the sleepers are too dangerous to carry down the escalator. So from day one, I had to revisit the LU track form completely with no budget to actually make it buildable. So I went from being a ballast man to learning about various things like resilient concrete very quickly. So it was a very fast learning curve. A lot of sharks out there, as you can imagine, in the world, trying to flog things which didn't work. And really, then LU decided they weren't paying level 3 managers for about 4 years. I left and set our company up, and I've been doing development for various companies, product approval, systems integration with civil structures, etc., to try and optimise. These are some of the things I've done. I work on and off for a company called Tyflex, which is the Delcor corporation outlet over here, Edlon Surgery, which is Level Crossings, and various other people just to help them on their way. There's a few things which I've pushed forward into different arenas, which I'd just like to go through. You've got no corporation thing to look at to start with, so hopefully we can get into engineering. Everything here is engineering, and the products I'm saying I'm obviously getting are prioritised because of my paymasters, but the same principles of what I'm talking about go through various other bits, and I'll explain that more as I go along. That was it.
No, we're not there. We've got the picture showing, but we haven't got the. What is going on?
I'm running from there.
We just won't move on. What the devil's happened here? Good, right.
We're leaving it like that on that one, are we?
Sorry?
Is that going out like that?
Jeremy, select the display settings on the top. You should be able to see duplicate slideshow. Yeah. We both see the same thing now. Yeah.
Oh, thank you. Well done. Thank you for that.
Cheers. No worries.
Right. For my pains, I got dragged into getting Delcor approved on Network Rail, which I've managed to get 4 base plates, one on the bullet version, so I'm not going to talk about that too much, but there is one available out there if you need it. So there's 3 types here, which we've got in, one for sleepers, one for long timbers, and one for slab track. So eventually I'll go through them as we are. There are 2 types of base plates. The one I'll talk about mainly is the AUK1 compression plate. I've got a slide on the high attenuation egg, which I'll explain later. But basically the principle of these things is you've got 2 bits of cast iron. So you get the cast top plate and the bottom cast plate. They're put into a jig, and then high injection rubber at a design resilience is pumped into the system, and they're chemically bonded together. So effectively you've got the same as a bridge bearing seal on those, very durable, I think LU have managed to break a couple, but apart from that, there was a few issues which compounded the forces it was seeing. Let me put it that way. So these have been around since probably 25, 30 years. Been used in Asia extensively because of the patent issue in Europe. I was instigated to bring them over into LU when we had the track form issues. I think they've been in LU probably 10 years now. There's about sort of 18 kilometres of these in track of various forms, apart from a couple of check curves. Automatic train operations has caused a few problems, but apart from that, they're all performing really well. They work on up to 125 mile an hour. We've had them on 40-ton axle loads in Australia, down to light rail, and we engineer the rubber for the operation requirements. The two core plates are basically the 417, which is a slab track one, and the 523 that fits on a sleeper. They're both identical. You can mix and match them. So if you're in slab track and you've got something you need to get round, you can just swap over to the 523. They're dual seat, so you can put 56 or 60 E1/2 rail in. You can fit them on bell, Roxanne bolts, and whatever. So the way we work it is we get the operator's requirements, the loading on the axle, speed, etc., and just make a compound up for what they want. We specify three ranges mainly, which I'll go into, but we can work in between there. It's a computer change in the mixing of the rubber, so it's a no-cost change. The latest one we've done, because what we found is with long timbers changing to FFU, is that the bending moments on the screw is getting shortened because you've got a lot stiffer medium there. So before in timber, you get a bending moment on the screw, probably about 1.5 inches or so. With the tighter media of the FFU, that has shrunk drastically. With the FFU lasting longer, what we're starting to see in Asia is failure of bolts at the interface, very slight lateral movement, purely because you're not seeing more movement, but you're seeing more concentrated stresses in a smaller area, and you're also having an item that's lasting a lot longer. So what we're looking at, we've tried this on LU, and this is on Network Rail where we're doing it. We made this plate especially up for narrowness to try and improve the life. I go into lateral resilience, but the lateral resilience takes the forces out, so that damps down the lateral forces. It's been very successful in Singapore and Hong Kong, increasing the life of the assets and reducing maintenance. Right. I'll briefly touch on the egg. It's used on LU extensively. Network Rail, we've toyed with the idea of putting on Network Rail. The trouble is the egg is a very soft base plate. The Euro norms do not accommodate testing of soft base plates. When you test a soft resilient fastener, as we did in LU, you have to go back to the old DIN methodology where you put a row of base plates in, because a singular base plate or two together with double loading on there will give so much deflection that and the speed of the cycles mean that after time it heats up and you end up with very slight tear failures, which, although they're not structurally damaging to the plate, it means they fail straight away. If you put in a long line and you put an overload situation in there, the rail bends as a beam both laterally and longitudinally, and the forces disperse down the railway system. So this plate will never actually see that peak load from the wheel rail interface. But at the moment, I'm struggling with getting things through that completely comply with Euro norms, and the thought of going into something that doesn't comply to any Euro norms and taking it through, I'm afraid, as a collective between myself and the suppliers and designers, we've decided that the cost return is not sufficient to take this forward. So although this is using LU, a lot of light rail systems, we've got it in heavy haul in Australia where it's taking 40-ton axle load, 200 million tonnes per annum, performed 15-20 years. That doesn't come into being evidence nowadays, unfortunately. So very good system. It's the original one where the Cologne egg was based upon, been obviously modified. Very, very good noise and vibration attenuation on it. Basics, noise and vibration. Resilience, we obviously, use. One of our things is noise and vibration. I'm not going to go into it much, but just to give you an idea of how it radiates. The all resilient systems will look at low frequency vibration. So wheel squeal, etc. They tend not to have a great deal of benefit, but it's a ground-borne noise. So from your tunnels going into the ground, they radiate into the clay, etc. Or if there's concrete structures, they radiate through them. They then hit the foundations, go into the building, and the building rooms then act as a microphone, which then sort of spreads the noise, and that's where you get that low rumbling noise. Planning now has jumped on this after Crossrail because they had a field day, so now it's coming in drastically. We've got to look at noise and vibration on there. Just touched on it because it will keep coming up, and this picture, it just gives you an idea of where we're going. Resilience has been something that, as I said, I had a very fast learning curve on it. And one thing that I think we all tend to get trapped into is we think that resilience is managing the forces vertically. It's not. It doesn't work unless you laterally get your resilience as well. A stiff lateral track will cause more damage on curves than anything. And the combination of having soft in one direction and stiff the other is a disaster where you get any minor flange contact. And I've got the scars to prove it. So all the systems really, if you've got a toolbox of items, and if you're on curves, you need to make sure you understand how your lateral forces perform and how you're going to manage that. Without that, there's been some very classic places where there are major issues. I won't mention any names in case somebody calls me over the cover. We've always, as I said, lateral is a minor thing. The other thing is that we're great for putting down pads, and then you get a bolt on there and you get somebody on a jackhammer, tightens it down, squashes the resilience out of it completely. So the resilience does nothing. By the time you get to the resilient area, you've squeezed the first half of the life out of it, and then it can't do anything. Even if it's set up properly, you do tend to sort of you don't get that same effect, because having no preload on a system when a train comes to it, the initial vibration hits it and it absorbs straight away rather than going into it. Fatigue points. One thing, again, I learned very quickly is you don't have any metal going through the rubber. As soon as you've got metal going through the rubber, it's got to bend. Laws of physics say it's going to bend. As soon as it bends, it's under fatigue. You can't monitor it because of its location. Therefore, it will break. When it breaks, we don't know. But if you've got a fatigue point, going through a resilient layer that's completely covered, it's unmanageable. It's something that you've got to be very careful of. Secondary stiffness and deflection control, that's the other thing you got to look at. What you don't want is like an elastic band where you keep stretching it keeps going. You have to get to a point in the system where you can manage it. So if you get an overload situation, it stops. You don't want to be like running through a switch where you break it, you want it. So if somebody chucks a 40-ton crane over it, the whole lot just sees it up solid, acts like a base plate, cast iron base plate, and then next train after it runs okay. The other thing that, again, we get mixed up between, and it's prevalent on a few systems, is rail roll and lateral shift. Rail roll is something you see on a classic sort of clip situation at the foot, where the rail tips over, pivoting on the outside. Handrail housing in a resilient system, that can be excessive, and actually you can lose your proper wheel rail interface on it, so your profile gets tipped over. So you also to look to make sure that when the train hits the system, it goes down and across rather than over. So again, that's something, it's generally abroad you can get away with a lot more, but in the UK we seem to have a lot more corners, a lot more issues. And the other one is making sure that the propagation of defects doesn't get any worse, and hopefully you can actually manage it better. That one is a minefield. We're well in space on resilient platforms. Some behave a lot better than others, and I will touch on it later. These are the classic issues. This is an extreme issue. On a light rail system, they put the classic. It was a grout pad, a resilient pad, going up into a bolted system. Quite light loads, about 8 to 10 ton loads. Over time, the bolt has started to rattle. It's fatigued in top, started to break the grout pad up, and the bolts are starting to break. So you've also got fatigue in the clip, and the whole track form is basically sort of going. That will unzip as you go along. So once you've got a weak spot, it will just slowly go down.
So is that a rigid grout?
There's a grout pad, and then in the middle, just between there and there, there is was a 20 mil soft pad. DLR, all the track forms of this ilk are on the danger list now for replacement, and it's not an old system.
No.
Just to give you some idea of N&B performance, it's one of these things that's a black art, and cutting it down to basics. I'm not going to say these are absolute figures, but it obviously depends on the ground carrying conditions. But a direct fixation, which is cast iron plate on concrete, you're looking at 3 or 4 dB. Embedded rail, that's your headlong type thing, typical tramway system, that's 6 dB. Resilient casting base plates, that's the alt 1, up to about 10 dB. Booted system, the LBT, up to about 10, but that on curves, it doesn't quite work quite as well. The egg system, which I talked about earlier, I have got it down to about sort of 18, but nominally looking at 14 is what we say is a maximum. And then you go onto your floating slab track, so effectively a ballast mat under, you're getting down to 20, and then full floating slab track, you get about 25. But yeah, so that's where you are. So really the Delcor egg is probably the best you're going to get without going to expensive floating slab track. And then you sort of got the LBT and the Delcor alt 1 as sort of following on behind. Again, with technology, we're fine tuning that, and we are getting improvements on that. But for a basic rule of thumb, that's about where we are. So this is the alt 1. Showing the graph is showing the rail deflection. The blue line is static, the green line is dynamic, and the red is fault mode. Effectively, that's an overload situation, so that's the maximum it will be. The idiot who put this slide together, who's me, forgot to put the scales in, but the maximum deflection on this one is 3 millimeters. I was trying to fit it in, and suddenly realised I've cut it out. But this is what you would see typically for a 17.5 ton actual load, 125 mile an hour. So it's quite a onerous input. Personally, I don't like deflection going above 3 millimeters. I think we're getting into dangerous territory after that. And everything in the UK, I specify that 3 mil is the maximum, because you can get secondary oscillation if you're not careful. On the left-hand side shows you the dB reductions we're getting for that train at that speed. So you can see, when we get down to 80 to 100 dB, we're getting quite a sort of significant reduction in ground worn vibration there. And obviously, once you get above sort of 50 or 60, you're starting to get into the zone where the wavelength is doesn't affect the ground, so it's getting more enjoyable and stuff. So it's quite effective for what it is. Pretty durable system. It's put up with a lot of stuff in the Sydney Metro. It's been down there for 40 odd years, and they've taken some out, tested them, and said you've got another 20 years life left in them. So they're doing quite well. This is a summary sheet, so I've gone to make sure I don't forget anything. Advantages: no fatigue points. We can manage resilience to suit the loadings, and and the sleep spacing, etc. the peak loading, as I touched on it, the rail is used as a beam, and as there's no preload on the rail, you don't get any uplift. You only get uplift caused by a pivot. If you've got no preload, you don't get a pivot in the system. So all these lovely old pictures years ago, you used to see of a heavy loco with a bow wave in front. You know, you don't get that scenario. That if you go back to the previous slide, which I'll try, you can see the uplift is probably about 0.01 of a millimeter, which is effectively the uplift caused by the weight of the rail resting on the pad. So yeah, that is laterally as well. So effectively, if you can imagine, I've got some graphs in a minute. It will the whole rail bends, so the rail deflection length is increased significantly. The rubber is natural rubber, so it stiffens with age. So as you get towards the end of asset life, you're not going to get this floppy bit of rubber in the chair. It actually stiffens up, so that although it doesn't perform and give you the NV or the fatigue reduction in the system, you're not actually in a case where you're getting in any danger. All you're doing is wearing your asset out quicker. Everything has been designed to use existing tooling and skills. All the clever bits we do in the factory. So as far as the guys on track are concerned, it is a base plate that screws into something. End of story. We don't want any whizzy stuff down there. We just want it to go on there and they plonk it in there. 40 years traffic, high N&V performance. And the other good thing, existing spatially constrained railways, London Underground typically, yeah, unless you've got a real, dare I say, a pig of a railway, it will fit in most places and work pretty well. So DLR, they're on a night shift, which is 3 hours. They're changing 20 base plates a night, drilling and grouting. So it's, you know, it can be done quite economically as well.
Where's that? Is that on the viaduct? Sorry.
The viaducts, yeah. I said about the bend radius, bend length, whatever you like to call it. This is a typical graph we did going back to my earlier days. So the percentage number there you're looking at is basically the wheel rail interface force. So by spreading the forces out, we're actually disseminating the forces. And we were in places getting down to 40%. I don't normally claim 40%, I say 50% of the loading at that point is reduced. But you can see over there, you're spreading it a long way, and depending on the stiffness and the speed, it will go further or less. So you're actually sort of, there's two things here. One is your load is reduced, and the speed that you load the railway up is also reduced. Again, this is more of a summary. Vertical forces. So if you could pass my bag over. Wherever I left it. Should be a carry bag.
Is it that rucksack?
Yeah, that's right. Yeah. With the base plates. Sorry for you lot at home. The base plate, this is a cut through section. Yeah. So you've got a cut through section there. The black bit is a rubber, that's steel, that's steel. So effectively, when you turn it upside down like that, you can still see that the forces don't go into the outer plate. So all the forces go straight down onto your formation layer, which is probably an HDP pad followed by concrete. So when the loading comes on this, goes down, and you're not actually putting any loading into the outer ring. The outer ring is there to hold it preloading position. So that then downwards puts massive friction on your formation, sleeper, whatever it is, and that holds it in place. So you're not actually putting much stress into there unless you get an overload situation. The rubber there, that's where electrical stiffness comes in. As you can see, it's different configuration because we want to manage the lateral force, hopefully is less than the force going into the sleeper. So that's thinner, same compound, but that allows that to move probably a millimetre and a half maximum before it locks up. So that then also gives you movement in bend that way, which means your lateral forces are also shared down the system. The idea of this, that's your secondary stiffness where these blocks are. So when you get compression, those blocks touch together and the system locks up. So that becomes your secondary stiffness. So you can actually manage the deflection down to your 300 meters maximum. I did an FEA on this system for a 60-meter radius curve on the underground Caxton curve. And we actually found that the highest forces that the bolts were seeing was caused by the preload compressing the base plate down rather than the train going over it. So that's the sort of magnitude of force reduction we can do. So you're actually, you're talking down to 230 kilograms is actually puts more force on the system than a train going over it on a 60-meter radius curve. Also, the other thing is your rail castings, pandroll clips, fastlift, whatever, they get reduced fatigue on them because the rubber's taking all the impact. So you get less fatiguing on there. With this system, particularly, what happens is the vertical load comes on first. So initially the rail goes down, and as the vertical load hits it, it goes across. So your rail goes down and across rather than rolling. That means the railhead profile stays in its optimum position, so you tend to get less rail wear. The egg, very similar, but it does tend to roll a bit more because of the way it is. The two systems work. Apologies for the acid band, but my glue doesn't work. As you can see, the egg works in compression and tension. So as it goes down, it stretches it as well. So that's why you can use both sides of the property of rubber, which gives you the greater attenuation. But because of that, obviously, it is more liable to roll. So it rolls a bit, but probably no worse than the pandroll clip. Railhead damage. We did some testing on DLR because we've just done a check plate for them with a Delcor, and the vibration reduction on the high frequencies, which tends to cause corrugation and propagation, was slightly reduced over what it was. So we're not going to increase the corrugation. We've had some issues with corrugation on London Underground. We're still doing major investigation on it, along with the damaged base plates, which I said. It does seem to correspond with ATO, ATP, alternative train operation. Although we've got no evidence and we're still working with LU on it, we do feel that probably the total consistency of driving now is a big issue in not breaking the cycle up. Having a driver who drove faster, slower, stopped slightly before a signal was enough to break that cycle up. It's something that's ongoing. We had the first track I put in there with the egg, it slowed down the corrugation. And since ATO, ATP, it's now sped up to worse than it was now. So it's pointing in that direction, but cards on the table, we're looking into it. Anything we can do to try and reduce that, we will. So we're doing development work, looking at see if we can work with LU to reduce that issue. Everywhere else, touch wood, where it is, we seem to be okay. Right, going on to other things related to its systems design. So stiffness transitions. Been a bee in my bonnet for donkey's years. Why we dig a big hole, chuck a massive great lump of concrete in there to stop the formation being pummeled to death. So instead of that, we pummel the ballast to death. And whereas my background in engineering, I've always worked to try and reduce or ease the forces off. This was done, a colleague of mine, Peter Stronstein, tried it in Sydney in 2004, effectively running off the slab on resilience. And then you've still got obviously the momentum of the movement of the rail, and then you come off it onto Delcors on the ballast. and then you slowly stiffen up the rubber. And as you can see on that bottom one, which I'll show you a bit further, in the dim and distance, you can see the change in the base plates going to green. Well, that's the different stiffness. But hopefully I remember the graphing. This is the first ones we tried, LU, which has become the standard drawing now. So you can see you come off the concrete slab onto the wider sleepers with the Delcors on at spacing, and then halfway down you change the green ones. Again, we don't have to change every single base plate, because using a rail of a beam means that as the rail bend comes along, it picks up the stiffer one and slowly stiffens the rail up as you go along. So you'll have, say, 10 sleepers interacting with all of them, then it'll be 9 one slightly stiffer, so that makes the rail stiffen up slowly. So rather than having every single one different, you can actually use it by rolling the rail stiffness down along and clipping along. It's a bit of a hard concept to take forward, but I think I've got some graphs further on. Right, that was just a recap, and I've probably already said all. Yeah. Brilliant thing about this is, intrusive works, you haven't got to dig a big hole, you're just putting in bigger sleepers in a different configuration. All the movement is kept out of the ballast. And one thing you've got to remember is that movement, again, is not only force going down, it's lateral movement. So what we found was that if you did it on something like, you came off a lateral resilient system onto a padded system with a soft pad to do it, what you was getting as you came off was the track would be moving slightly because you got lateral resilience in the system. So very slight movement, only 0.2 of a millimetre. That was rolling into contact points at the ballast slightly and just knocking all the cohesive bonding off the ballast. So he's ending up with that critical layer of ballast underneath the sleeper had lost its cohesive bonding, and you ended up with marbles there. The tamper comes along, hits it, and they spew out everywhere. So by also managing the lateral resilience as you come out, gives you a way of increasing the ballast life. The aim of this was to make sure that the transition life was equal to or greater than the life of the track it was running, balanced track it was running into. So the idea is that we reduce the maintenance interventions completely and reduce the risk of twist errors, etc.
What about stiffening the ballast up with epoxy resin and so on the transition between the slab and the ballast? That's been tried and done.
That has been tried. It's varying success. Again, you've still got that issue with the breakdown of the ballast very close to sleeper. And the problem we had, and I did it with Darren at White City, we put it in there, and when it failed, which it did after about 4 years, we was in major trouble. Because it breaks off in big lumps and the whole track just started to go everywhere, and it was effectively a complete renewal. So potentially it can do it, it will help you out, but once you get a failure on it, you're in trouble. And my view is you've still got interventions, you've potentially got drainage issues you're blocking up with, and it's really just trying to keep it as simple as you can. This is work.
Well, you want. Forgive me,
No, it's fine.
You want block drainage up and so on if you're using the right the epoxy resin for the strengthening of the ballast. I don't get gluing the ballast.
Yeah.
You can call it gluing if you like, but it's not actually gluing the ballast. It still stays as a, if you like, not a homogeneous system. It ends up as a system which is somewhat flexible. Then it doesn't break up.
No,
If you're in places like the old Bletchley South Junction, for instance, underneath the east-west flyover and so on, and lasted well until the junction was taken out, quite frankly. And you can replace it if it starts to deteriorate. It will break up without having to take the track out and so on. It does, and then you can reinstate the epoxy in it and bring it back to its original state.
And I put on areas like that where you've got S&C, which is going, where you're not transitioning in between two track forms, it works well. Like you say, it is very manageable. Where you're coming off a fixed structure over short length. Yeah, I've used ballast loom anchor, but I never use epoxy flexible stuff.
Okay.
But you know, everything I've seen done, it's just the damage it does to that layer on the sleepers, even with an anti-wear pad on there. You know, it's just that rocket motion.
Yeah,
I suppose.
I'll go along with that.
So yeah, I fully agree with you. Where you've got areas which have take high impact, like PNC or flat crossings, etc. Yes, definitely. I wouldn't use Delcors in that situation anyway. The only time I would recommend them in ballast is if you're coming off a resilient site onto a ballasted track form, so you can manage it using the same instruments effectively.
Yeah, there's been one or two places that it's been used where the slab in itself was actually part of the problem. I'm talking about on the original Thames link.
Yeah, well,
in
you've
the
got
West Hampstead area and so on.
Yeah,
Where
well,
the
you've
slab
got-
is suspect as well.
Oh yeah, that was a bit interesting, isn't it? But where you've got a fixed system on the slab with no resilience, I wouldn't recommend running out onto a Delcor system because you're going from a stiff, soft, then back to stiff again. So it's really to manage the change in stiffness on a resilient track form to a ballasted track form without major interventions. So I think we agree with each other. But yeah. Where have we got to? Done that one. Low installation costs. So basically, it's the same. You know, if you're coming off the end of a slab, you've got to replace the last panel. So it's the costs are basically minimal. And potentially, if there's change stiffness, you just with the vehicles, you just unbolt and rebolt different ones on. These are a couple we've done. That's the first one I installed in 9 years ago. That was on the Met line. That hasn't been follow-up tamped. It was supposed to have done, but never did, and it hadn't moved. That's coming off of 22 kilonewtons onto 35 kilonewtons. And the other one is in Kent on Stour Bridge, I think it is. That's 80 mile an hour running, coming off a newly installed concrete bridge. And in the distance, again, you can just see the change. The network rail one was a test site. We've done a lot of testing on deflection, what it's doing, and it's performing, luckily, as I designed.
Yeah.
Long timbers. I've gone on about FFU and side cut, etc., about the fatigue. The one on the Sydney Harbour Bridge was done 25 years ago. That was done as to try and stop the vibration going into the bridge and upsetting the neighbours each end. Worked really well. The timbers actually failed before the Delcors did. Major upgrade on rolling stock going on now, so they're replacing the timbers, and that's the only reason they're coming out. The middle one is Norwood Viaduct. That was the first one we tried. It's going on to conventional hardwood. Again, Sussex did some testing on it. It's performing as required. And the other one is on FFU. That was done on a heritage railway for testing. I'll show you the video at the end of resilient track form, how it works. I won't stress somebody out at the moment for changing the slides over. Again, that's working really well. I'm trying to sort of get more people interested in using the Delcors with the FFUs, but with the cost restraints going on, they seem to the bean counters seem to be stopping a lot of, how I say, enhancements that will give maintenance a big benefit.
Delco and FFU is quite a good solution.
It's quite a good solution. Their view, they've done probably 15, 20 bridges, I think. We've done some on Network Rail, we're doing some more, but it's just, yeah, it's hard work getting the word out there now. I have, this again is a wrap up one more stuff I've said about the resilience. We went from, in the old days when I first started, we used to have that marine softwood as long timbers, which was beautiful timber. Worked a treat, used to be really forgiving, really good. Then went to hardwood, and now we've gone to these sort of composite ones, which are brilliant, but how far off we are putting a lump of concrete in, I don't know. The newer materials basically have no meaningful resilience. They can engineer it in, but very rarely do they. It's pretty expensive stuff in its own right. As soon as you start modifying it, the price goes through the roof again. So especially on minor curves, etc., you will see lateral failures in about 15 years' time. I don't know anybody who hasn't been involved in long timbers who haven't got a sob story to say about them, how they've failed, how they've had a derailment, how gauge widening panics, this, that and the other. Very high maintenance liability area. So by putting the resilience in, you reduce that liability. With the inability to get out on track now during traffic hours means that you can't actually go out and see what's happening. You're relying on cameras, people going out at night time and pushing things. So anything we can do to sort of reduce the potential failure mode now, I think is something we should be looking into. And also, again, I just said there, the peak force is overcome. When the video comes on, you'll also see that how it works, what happens. And with a system like this, what you've got to realise is that this will effectively take out the unsprung mass damage, because you're effectively putting another layer of suspension. In fact, it's not on the train, is irrelevant. But as far as the formation sees, the rail will still see the unsprung mass damage, but the structure below it will not get that unsprung mass. So when you've got heavy freight, dodgy wheel sets, a lot of that damage which is going into formation is taken out. I left this slide in mainly for the picture in the corner. We're talking about dual resilience again, but that little picture in the corner is something that John and myself are working on a project at the moment. I've done it abroad. Basically, you've got the resilience in the system, so there's no reason why you can't just bolt it straight onto the girder. This has a great benefit. I've done it quite a lot in the States and Canada, where they've actually taken the timber off, jacked the bridge up, replaced the bearings with the grout, and then put a bearing on top. So we've lifted the whole lot up 300 mil, bolted the bolts back on the existing structure, and gained ourselves 300 mil clearance. Also with John at the moment, we're working in some areas of flood. We're putting on top of the bridge so we can maximise the flood opening in all directions. If you've got the resilience in the system, the timber is always left on there, and FFU is deemed to be a timber replacement. If you build the resilience into something else, why do you need that timber? Why do you need that extra interface, that extra set of bolts, that extra medium? What benefits are it giving us? I know it means you've got to work with civils guys. I might work with civils guys.
What's wrong with that? What's the thickness of the resilience between those base plate and the top of the flange?
That much.
Not much different.
Yeah. So effectively, that is the same as a grey iron. It's SGF, so we can reduce the thickness on this. The same as a grey iron, it's about 44 with a pad on, performance pad on it. You're looking at about 50 millimeters.
You said those small rectangles underneath would compress. Are they elastic? Do they reform after the loads take off?
So they reform, and obviously the heavier the load, you change the configuration accordingly.
Yes. Right. Okay.
Again, I think structural vibration potentially, because I worked with one of your old colleagues, Mr. Besant, on this one, which was yes, and he was right up for it at the end.
What direct fix to a girder?
Yeah.
Very interesting.
Yeah.
Well, I know.
And he was saying,
good lunch, did it, Peter?
Basically, he was saying that with this system, if you manage the resilience right and you don't get any impact, you can potentially spread the load, and on certain structural timbers, on certain structural bridges, you could actually increase the loading on the bridge. Because
noise factor though.
Sorry?
What about the noise factor? If this is droning right through the whole girder of the bridge, isn't it? If it's plated, if it.
Well, no, the resilient layer will take out that vibration. So that resilient layer will take out the vibration that's going through it. So all the groundwater vibration going through there. And the modelling that Graham looked at did show that, obviously you have to assess every bridge because every bridge is different. But there was a significant advantage on some bridges to looking at this with or without timber on. He said with timber it will give you a benefit, but he said you can get the same benefit if you just went straight on the steelwork.
Reduced dead load?
Yep.
But Peter, how about the track structure interaction, the expansion of different thermal expansion of the bridge versus the track and
what we did, I did a fair bit of work on this on it was on the East London line. We'd have to look at using low toe load fastenings or zero toe load fastenings and fixing in certain areas. Probably the Voslo system is better to do that.
So you think that you can apply the same thing here? I was the design manager for East London Line. I know. This is Siva here, Peter. Thanks.
Okay. Oh, I see. No. So
it also reduces the possibility of corrosion on the top flange of the beam because you're not got a wet timber on it.
that's right. Yeah, that was one of Graham's big benefits. You reduce the corrosion effect on them.
You can see the top.
Yeah, you can see it, and it makes the inspection so much easier for everybody. And the big thing is you take out one maintenance interface layer. All your bolts. You've got adjustability with the.
Yeah, but most of the wheel timber bridges have the corrugated sheets. I think this one may not work for that. And then the level different, Peter, because the buildup of the FFUO timber on a steel deck. So how do we create that extra height?
Well, everybody's going to be different. Everyone's going to have a solution. We can pack up to 25 mil on the HDP packers. From there onwards, you're really looking into putting a box frame under or something like that, aren't you?
That's interesting.
It's got potential. The other thing that Graham, which we didn't look into, Graham said you could replace the timber and actually put another structural member in there to increase your brick strength. So replace the timber with a structural beam in there, increase the strength of your bridge, and put these straight on top. It's something that I think has got a lot of mileage. It's not going to work in every situation, but I think it's something that we should put as a tool in the toolbox that could save us, potentially a lot of money in certain areas.
Is this being installed in?
It's you're putting first one in this country goes in hopefully this summer.
Yeah. Oh, so it's
The bridge is it's a second-hand bridge that's being prepped up at the moment. We're waiting for the Environment Agency to say that the newts are no longer a problem. We'll go in.
Waiting a long time.
Yeah.
Is this on a heritage railway?
This is on the Heritage Railway. It has been installed in Hong Kong, Singapore, and places like that. So it's in action. So we've got the data to prove it works. Happy if anybody, once we've got it installed, because it's Heritage Railway, we can get possessions easy. Go down there, do some modelling, do some, assessments on it, whatever you like. So it's going in definitely, and hopefully by the winter it will be in there, and we can get trains to it, so we can run trains to do some monitoring on it. Unless you want to go to Australia or Singapore or Hong Kong, which everybody seems to, but anyway.
The Singapore FFUs are on ballasted track, Peter. Actually, as part of the work, it was done by who did that? Balfour Beatty, and we went to the Japanese factory to inspect the FFUs and all that. It's 3 or 4 turnouts on FFUs.
Yeah. There was some on I can't remember which line it was on. I know Peter Stronstein was telling me that
Northeast line, yeah.
Yeah, so it has been done and it's working. They've done it on some coal haulier lines in Queensland as well, I think. But yeah, no, it is something. Yeah, I agree. It's not going to be every bridge and it's not going to be the end solution, but it's potentially, with good design, it's got a lot of mileage, I think.
Interesting.
Done for much, don't we? Also, we do what they call eggs for turnout. So these are these massive, great, resilient things that you clonk on. So the pictures I think are from New Zealand coming out of there, one of the first ones they did it on. Obviously, when you go to flat bottom rail, which is pretty stiff, put it on a lump of concrete without any resilience, with all the impact forces, you tend to get significant failures, which, yeah, Victoria Line was a bane of my life. We changed one over at Walthamstow, few issues on there, but I think that was the first of type. It seems to be bedded in quite well and firming up okay. No major issues as far as I'm concerned. A bit of uneven rail wear, but on a sort of 36 million tonne per annum railway, on a tight turnout like that, so there's a crossover, I think you're always going to get them. We've got about 8 or 9 of these in on the underground. They're working well. We've also, on the underground, we made the slide chairs actually a Delcor, so we fitted a Schwier slide chair into a Delcor and bonded it in there, which again to take the moving parts out of the area. And also, as you see in the corner, we've done a check, both vertical for check curves and no, inclined for check curves and vertical for S&C. And there in there, we've done an adaptation, and that is actually the one we've done for DLR that we just put the first site in. We're doing the testing on. I think there's about 12 or 15 check curves on LU with this system on, down to 91 meter radius. They all seem to be performing okay. No issues with anything apart from I think there's some geometry issues which are caused by excessive wear. Probably a little bit more maintenance needs to be done on keeping the check gauge and flange wear gauge right. But no, apart from that, they seem to be performing pretty well. You've gone from an asset life of probably 15, 20 years, and at the moment, I can't see any reason why we can't get 40 years out of it. So it's a significant bonus for the underground. As with all these things with the underground, especially with ATO, ATP, high performance traction motors along with very stiff bogies. Yeah, it's a recipe for disaster. So, but you know, we manage it. Yeah, we have been managing it, and the new crew are getting up to speed with what they've got to do, and hope they're taking it forward. Right, we're moving off of for the moment and talking about embedded rail. I got involved in this basically for the approvals. It'd been approved for a long time on Network Rail in its old form, which was a massive, great lump of concrete, about 550 mil deep. It wasn't viable to put in because you hit services every time. So it was redesigned down to 350 deep, top of concrete to bottom, and then went back through the approval process. It got stuck in product approval. The only change was the concrete. Performance was identical, and it took 3.5 years to get through. So I dragged it through the last bit. So effectively, what you've got is concrete sections. That's the grey bit, and then you've got what is basically a conventional formation underneath it. So you've got type 1 and then a sand binding layer. The reinforced concrete with the road grip surface on it, and then you bond it in, and you can see the rails there are bonded in with a chemically bonded Corkalast. Again, that resilience is built up by user requirements. You see that here's one I bought earlier. So effectively, what you've got here is, assume that's concrete edge, you prime the concrete edges, work out your finite level, so you're always going to have a level differentiation when you put these in. That's your finite. You've got a resilient layer there, that's your inclination, and you put packers in there either way. But it doesn't show up very well, although you can see it on the slide a lot better. You've got cork-glass wedges, which is the same material that you put it in. You've got round the outside these void fillers, which effectively just save the material. That's where your money comes in, is that material. So they put these fillers in there, and they have a racking system, which means that as you get your finite level, you just tap these wedges in, and that gets your correct alignment. As you can see, apart from strategic places where you put these pads in, it's free under there. So you fill up one side, it flows under, back out, levels up, and then you top up to get your level, sets off. Once it's in there, you have to get it. Anytime you replace this is railway. If you get a contamination, D is always probably the only thing that will cause you issues. You then mill off the first 30 mil, either side of it, top it up, and away you go again. So, yeah, the critical bit is getting it in right, temperature, moisture, but that's something that is controlled by process and training. Once it's in there, I had the first one that went in was about 20 years ago at Croxton after a derailment, because panels possibly wouldn't work there due to that. And the guy rang me up and said, "We've had it in for 17 years. We haven't done anything. Can you come out and have a look at it?" They did have an issue because where the water had run off the edge, they hadn't cleaned the muck out, and they had this pile of sort of slurry, which was full of salt, and it had done it had a defect on the foot. But apart from that, it was performing really well. So realistically, inspect it once a year. If your formation's good, you just won't go. You can do ultrasonic inspection a lot with it. It's the likelihood of rail breaks or fractures is minimal because it's fully supported. I've done a cost benefit analysis of it with Network Rail, using Network Rail figures, but it costs 10% more to put in, but that pays back within the first 2 years. And again, we put stiffness transitions on this, and we've taken a place at New Haven, which is a test site where they were going in every 3 months to restore line and level. We haven't touched it since. And that was start of COVID. So it works really well. And quite ironically, Heritage Railways can put these in cheaper than they push trails in. Yet Network Rail can't. There's more going in on Heritage Railways than there are on Network Rail.
So on level crossing.
Yes, level crossings, and obviously the same principle on things like tramways, but also, you know, we do pits as well, and they're brilliant for pits because you have a cut off down there, so your core glass will come along up there. You put a temporary former there on the edge of the pit, so your pit can finish at the edge of the railway. You take all your sharp edges out. Cleaning is easy, no corrosion issues. Yeah, you get an extra 300 mil on your pit, and you also take away all your knuckle backers. Works really well. But yeah, we're really struggling to get this in on Network Rail. We've got conventional panels with 4 metre or 3 metre. 3 metres, we've gone down to 125 metre radius, just by tapering the ends because there's enough room in the channels. The rail section is obviously drives what your channel size is. So if you've got rail like that, you don't need much. And as you get bigger rail sections, you obviously widen it up. Formation requirements are the same as you would put down for new track. So 100 kilonewtons, 100 megapascals.
Assume you've had highway approvals for these then.
Highways approvals has got it meets EN standards on grip. It's fully approved for Network Rail. But we had Foxton, it was going to go in, and a beam counter came along and said, "Oh, Strail's cheaper." I said, "But it doesn't work. You're lifting it every 3 months. Doesn't matter. We've got to deliver something compliant. So therefore, we're not putting this in. We're saving 10%. And we're going to put the Strail back in."
Where's the bean counters?
Yeah.
Seem to be blocking it.
Yeah.
Not this whole life cost view.
Well, all I've got to do is, I'm afraid at the moment with this sort of
Yeah.
best cost, it's gone out the window. You know. Works delivery seem to be a lot more receptive, but capital works are driven by cost. You know,
Immediate cost.
immediate cost. Yeah. Yeah. It's not individuals; it's a system, and you know, the interpretation of the system. So there's a sort of breakdown of it easier. You can see we've also got it approved for a check system. So we've got a tight curve, which again, that's project's been delayed about 8 years now, I think, which has got a check curve in it. So we designed a block system so you could embed the check curve around there without a break. Obviously, a bit more costly and quite interesting, making sure you get the bolts in the right place when you curve around. But it's doable. We assume 40-year minimum asset life. That's worst case scenario. It's always road transport that kills it. But basically the stuff that's in Holland, it's on very poor ground conditions, has been in there 40 years and not showing any sign of degradation. Rail replacement, hopefully I'll put a slide in. Yes, I do. Rail replacement is done. As you can see on the base, you've got pad there that is not bonded. So that's not bonded to the concrete. So you've got the big pizza cutter, which you put down the side and then just lift the rail out, clean it all up. You don't have to clean the material off because it will bond to itself quite happily. Just take all the degradation out of it, rebond it back in again, and in you go. So that's a nighttime closure to do it.
What's the curing time?
Curing time for works vehicles, depending on temperature, is maximum of 1.5 hours, about 3-4 hours, full line speed. So yeah, it's not an issue because by the time you've repaired any bits and pieces on the road and got your hand your track back, it's fine. The other thing, I'm doing quite a bit of work on the continent where they're doing electrification, etc. We're putting these underneath bridges to save strengthening up the foundation. So if you look on the left-hand side, a conventional ballasted track, assuming your formation is good enough for ballasted track, then effectively you can rip the ballast off, put a binding layer down, set your slabs in, and drop yourself about, let's say, 360 millimeters without any major works. And because you're at bottom of formation level, your drainage, should, if it's effective now, it should remain effective. It's an easy, cheap way of doing it. I wouldn't recommend it for extensive long runs because obviously changing rails is always going to be a liability compared with that. But for small, 20-30 meter bridges that you want to lower under, it's not the end all. It's not going to be used everywhere, but it's definitely something that I think should be in the toolbox that we can use. And this is where my systems engineering sort of comes in. Luckily, Edelon, Cedra and Tyflex, Delcors, are sister companies who don't get on very well together, and I was brought in by the parent company to try and rattle some knuckles and get them working as a unit. This is where the stiffness transition. So obviously the Edelon Cedra is again a resilient track form. So what we've done is run the resilience out onto the black Delcors to maintain the deflection, then using the green ones, which are stiffer, slowly increase the stiffness until we get back into full ballasted track. Every one we put in, nobody's said anything about them. Everything we've gone and tested and revisited afterwards is performing well. So, the proof to me is when nobody complains. When somebody complains, you can go and sort it out. When nobody comes back to you, it's generally working. The New Haven one, the Swine's Head one, were done in very poor conditions and they're behaving well. The crossing itself at Swine's Head had a few issues, but that's basically down to ground conditions, and there's still a few hiccups going on there which need to iron out. But the New Haven one, which again is on marine alluvium, we dug out 500 millimeters of type 1 binding layer, put it in there, and after 2 years of TRB trace, you couldn't notice the difference from day one to the end of it. So it has worked, in those conditions, and the maintainer's made up with it. It just doesn't go back there like he used to. And this is one again. It's on the Heritage Railway, and this is what we can do. We can play with the complexities. You can use anything over 12 meters. You assume that the Edlon slab is a fixed point, so you can stress in and out of it. So you can, stress your S&C out of it, stress you out of it. But this one, because of what it was, we ran the twist rails and actually put them in the Edlon crossing to make it work. So these are the things you can do. Basically, once you've dug the hole, putting the slabs in, bonding the rail in, and getting ready to hand back for the tarmac is probably about 8 hours. A little bit more for a twin track, but it doesn't go up exponentially because you're already mobilised. If you're underground, you've got very poor conditions, which we have to do at Iron Acton. It takes a bit longer because you're pumping grout in through the system, which is not easy. We try not to do that unless we absolutely have to, but it does work well. So you're not talking about, what you're doing, major works. Where we've got a bad reputation is that everybody wants to use these in absolute dire locations. So you end up with service diversions, new drainage because it's sinking, major deformation digs because it's crack formation, or somebody wants to recant the track through, they only lose half a day. And you always end up with them going into very horrible locations, and you always end up being classed as expensive. But when you actually cut it down and look at it, it's not. It's basically because everybody's saying, we can't make anything else work. Let's try this. I'm also doing some work on high frequency damping. So the classic damper is a big lump of rubber on the outside, generally layered. It tends to sort of try and burn a bit off. It hasn't been that successful. So there's a guy in Hong Kong, and there's myself and a few other guys who are working on the system. And what we're looking at is making sure that we can take, again, it comes down to this, utilising every direction. The conventional ones, effectively, anything radiating out from the web at 90 degrees can be captured. Anything coming out anywhere else tends not to be. So what you have here is the white bit in the middle is a weight, and then 2 bits on the outside are cartridge. Sandwiched in between there is a layer of polymer, and that polymer is aligned to the weight of the white bit in the middle, and that then effectively works like white noise. What do you call it? Is it white noise? Where you get 2 amplitudes, oppose them opposite each other, and drive them in. So effectively, you damp it down by burning the energy off, by reversing the amplitude as it goes in there. We've done all the pre-production testing. It works well. We've got a site going in on DLR, hopefully in April time. This is aimed at high frequency noise. We're aiming in the 200 to 800 hertz mark, which is where corrugation is prevalent. So we're picking a corrugation site to actually monitor the reduction in corrugation. They're easy to fit, as you can see. They're a spring system, clip on really easy. Hopefully, if somebody asks me back in a year's time, I can give them some results.
Do you think they might do something about in-car noise as well?
In-car noise, it will reduce in-car noise by default, by effectively the fact you're not increasing. High frequency will be lower, but also the corrugation, which is one that rail roughness is a major input into in-car noise. It will reduce that or slow it down. I'm not going to say this is going to kill corrugation off. It won't kill it, but it will make it more manageable.
Increase the frequency of rail head
Yeah.
treatment.
Yeah. So what they do in Hong Kong with this is they actually put it in the areas where they get corrugation, which then slows the corrugation down to the same rate as a plain line. That means that they can program in linear grinding rather than going in, hopping about all over the place, doing emergency works. The other thing I'm working on at the moment is the Australs, which is effectively a competitor to Schwieg. They're not looking to take the Schwieg market on new build. Basically, this is retrofit. They're very, very easy to retrofit. I can do one in about 2 hours on site. You don't have to move anything of the point work. So it's effectively unbolt bits, screw them back down again, tension up, put a preload on there. So as you can see from the video, that's actually working, which surprises me. When the switch goes along, you also get an uplift from the roller. That also helps on getting your residual opening down, especially on the end of the planing. I did some tests again with Darren on the F switch, and we managed to get it to work on a hand point and get it compliant. So the way this works is you've got a spring down below, which the roller is suspended on. You preload the switch such, not enough to lift it, but enough to, as soon as it starts to move laterally, it lifts it. So effectively you get an instantaneous lift. We've got loads of these on DLR performing really well. Place like Canary Wharf, which is seeing massive turnbacks, etc. Guys really pleased with them. They go out, they can get one of these installed on night shift and hand it back. Work pretty well. They're very, very durable. Let's go through the thing. Retrofitting is probably UK where it's going to be big. There's nothing, you change nothing on the point work, and theoretically you don't need signalling input. All types of sleepers, concrete, steel, etc. Composite. We've designed it, I've actually designed it to fit on the resilience system, so it fits topside the resilience, so that it's not affected by the deflection caused by the train. Rail profiles, you can use anything. On the continent, it's on high speed, 35-ton axle loads. If you get a run through, it won't put anything in fatigue, so it's completely usable. I've actually put it in on spring points on LU, and they're running through because the train drivers won't get out of their cabs, and they're running through with train moves. It's been there for 4 years, nobody's touched it yet. Normal inspection is yearly, so it's low impact. This is one in Germany. It's in a steel mill. It's been in for 15 years like this. Extremely good bearings. It's a bearing company, not a rail company, and it's worked in that environment for that long, and still performing perfectly okay. Then that's enough of my blabbing for now. Any more questions? We may or may not have a movie to watch.
It's on the eggs,
Yeah.
which I think they used to call Cologne eggs, cloud eggs. Yeah.
Yeah.
So
Yeah.
is that's the origins of all these Delco based bases?
Yeah, the origins of this was that the eggs were made, Kloof eggs were made, and then Vosloo bought them out, effectively to kill the market. And in a bundle of stuff, Vosloo sold off a load of stuff for Asia, and in that was the Cologne egg. The guy, Peter Stromstein, who bought this, said, "Oh, I can sell it in Asia." So he then adapted it because he was into rubber, into heavy media separation, rubber belts, etc. industry, and then modified it the Australian market. It took off there, then it took all over,
And then sort of came back.
and then it came back. But it couldn't come into Europe because it was controlled by contracts. So Europe was excluded from that. It was still under Volvo. And it wasn't until a few years ago when it poured onto LU that the contract actually ran its time and was broken.
I have a question about the Edelon slab.
Yep.
Is it the per meter length? What is it heavier than ballast and concrete sleepers?
Yeah, it's
So,
because it's solid concrete. Yeah. So you're looking, it's probably about a metre of track is probably about a ton and 3/4. Yeah. But your ground pressure is reduced because you got continuous coverage. Right, this is FFUs. This is showing how the resilient platform works. You can see that's a 17, it's class 33, I think 18 tonnes, I mean. And this is like a slow motion. So you can, I'll show, when we show it again, I'll show you the spider on the side. The spider doesn't even get rattled off there. You can see the spider's just going down the side now. You come back up again. The spider's not rattled off that's the sort of thing. So you can, if you look carefully, you can see both the lateral movement as well, but you can see effectively that's the same as you've probably got more deflection there than you have on the secondary suspension on the train. And this is one of Graham Besant's.
Sounds about good.
You can see, yeah, because there's no preload on there, it's
And there's no sort of fatigue on the holding down.
so you can see with that spider on the side, it's not, you'd expect it to sort of run a mile, wouldn't it?
Yeah,
If it just
yeah, that's very interesting.
Yeah. So yeah, that's where we are with it. I think, well, I know I'm biased, probably. I think there's a lot of potential for tools in the toolbox here, and something that I think
Absolutely. Nice job.
Peter, usually the wheel timber bridges are noisy. Have you done any noise measurements before and after, or noise and vibration readings before and after?
We've done some, but they haven't been that scientific, because the problem I always get on noise sensitive areas, when people stop complaining, everybody's petrified to go back in there and do some measuring in case you haven't met your requirements. But I know we put some in your bridge, Mr. Ebbott, Baker Street, Finchley Road. What's that bridge?
R3, is it?
Yeah.
Yeah.
We did some modelling with Southampton on that, and we did show a reduction on that one.
And that's FFUs you put in.
Yeah, that was.
Short timbers, weren't they?
That's it,
Short
yeah.
timbers between the cross
Yeah.
burners.
Yeah.
And it was always a challenge for me, what were we going to do with that? So
Mhm.
you put FFUs with Delco.
Yeah. Yeah, the modelling showed that it gave us a significant reduction, but I would welcome the challenge from somebody. We've got this bridge, which we can go and do some monitoring on. We can look at the vibration within the rail, the vibration within the girders. This is an easy one to do because it's heritage. I've got full access to it. I can get trains to run on it when we like, what we like to do.
MR3.
Yeah, I'm after it.
Over a canal between retaining.
Yeah. So the modelling says we do get reduction, but we've never actually got around to proving it. The proof has always been that the phone stopped ringing.
Yeah, indeed. Excellent. Excellent.
Can I just ask you about it in general about embedded track systems? I got involved at one time with the Alpha Beta system that was developed. One of the things with that, I suppose its drawback as much as anything else, was that it was a redesigned rail, but it did encompass a lot of the things that you're talking about tonight in terms of resilience and so on, mainly with the way that the rail sat in the in the space in the however the slab was formed, whether it was formed as a continuous slab,
Yeah.
or whether it was like the Sursa systems, those sorts of things. What's your sort of opinion of that? Did it actually meet the requirements as far as resilience and so on?
The not having my Edelon hat on, I've thrown it away at the moment. But my view on life is that you only embed rail where you've got interfaces that require it. Rail replacement is such a pain in the neck that I don't think you get the benefits you need to do it. So I'm a great advocate. I like, resilient track forms, I think are brilliant, but it's just, you've got to make sure that the maintenance liability, and that is always the one that, and I was the one who was always slung on NU about the BT embedded track system. The systems interfaces didn't work very well on it as it was, and it was basically, at the moment I can send a gang down there on a 4-hour night shift and change 91 metres of rail. What do I do with this? And that was, throwing away all my allegiances. That is my mentality. I do some engineering for Edelon over here, quite a bit, some pieces, but I would recommend putting in needlessly long lengths of track.
So discrete crossings.
Discrete crossings, if you, and also the Irish have used it for bridges where there's weak bridges that made a concrete structural slab on top, and then you embed it into that slab or a channel, a metal channel which they've embedded it in.
But tramways must be, street tramways must be.
Oh, we got loads of that,
Embedded rail, aren't they?
There's that triple junction in Birmingham that went in, that triple double junction.
It's a new one.
Yeah, new one.
Yeah.
That was all precast. That was a nightmare. Oh, horrible. 28 metre radius curve, 200 metre radius vertical curves. Yeah.
We'll see that sort of, we'll see one side of this open, isn't it?
Yeah, that's it. Yeah. At the moment they're doing the Wensley Bridie Hill extension. They're putting the stations in with Edelon.
Okay.
We put them in on vertical curves. The last one we did at Northiam, that went in 1,500 metre radius vertical curve. So,
But it appears that the systems are all there to do exactly what you've been saying this evening. It's the big problem always is the interface with the existing thing. That is always the problem.
And with my design, I'm always very conscious that I don't want to take a problem away from one item and shift it 10 metres down the road to fit its object. If you've got somebody lifting across and you don't want them coming out the same frequency to mess about with the stiffness transition. That's the way I always sort of try and design things. I'm told I'm not commercially cute enough, but then my view on life is if it works, people come back. If it doesn't work, they won't.
If it works, I'll fix it.
Well,
Okay, is that the
Excellent.
last of the questions? Time has run on, probably due to my incompetence. So my apologies to everyone, but thank you for the voice from heaven that told me to click on duplicate. I don't know who that was, but thank you.
is this recorded or do I need to send a PDF around?
It will be recorded and PWI Central will ask for the slides to put onto the website. So
Okay, that's no problem.
I've got them there, so
You got them, that's fine. Yeah.
you're happy with that. Peter, thank you very much. Malcolm, could I ask you to do the vote, please?
Well, speak about the errors and so on. Peter, it's been quite fascinating tonight. It's nice to look at some of the unsung part of the railway. We always tend to be looking at the big picture, the big jobs that are being done and so on. In actual fact, all this sort of thing is vitally important in terms of not just fixing the problems and with our neighbours, those sort of things, but you're looking ahead and saying, we don't have to maintain this, it will last, it'll be here in 30, 40 years' time, and we won't have had to have done anything except run the inspection train over it, that sort of thing. You're doing that sort of thing, and especially with things like level crossings, the interface between S&C and the plain line, coming off bridges, all those things are the things that cost us a lot of money over the years. They're the places that we have to keep looking at, and they have caused some serious derailments in one or two places as well. So pretty good work that you're doing. All power to your elbow with some of the stuff. Thank you very much for coming to talk to us tonight. We've all very much enjoyed it.
Yeah.
Enjoyed it.
Excellent. Before I say to Richard, just at the next meeting, can I ask those at home to make sure when they've finished to actually leave the meeting so that it stops the recording? Because unfortunately, on the previous occasion, somebody didn't leave the meeting and the recording was still going 4 hours later. When you have finished, please leave the meeting on the big red button in the top right hand corner. I'm sure you'll do it better than I did. Richard, next meeting, please.
As you can see on the agenda, the resilience theme continues, but on a much larger scale. Mike Holt is visiting us from the northeast to tell us all about it.
Okay,
And I shall be with you.
that just leaves me to say thank you to everyone for turning up tonight. Thank you for those who are still online, for joining us online and bearing with the IT nightmare. Thank you very much, and we shall look forward to seeing you on the 5th of March. And maybe we shall retire for a suitable refreshment at the Three Guineas afterwards. So maybe.
Thanks, gents. Thanks, Peter.
Thanks.
Thanks, Ray.
Thank you. Bye-bye.
Rodney, is that your diabetes alarm that keeps going on? It's driving me insane.
It is going off.
Excuse me, but you need to leave